continue with this afternoon session. So now is Mairi Sakellariadou from King's College that she's going to give us the theoretical point of view about the gravitational waves.
Okay, hello to everyone. Can you hear me well? Not very. Can you hear me well? I don't want that becomes too loud or too. Exactly, but because I checked before with this control, I want to be sure that is the right one. Anyway, so thanks a lot for the invitation. It's the second time that I'm in Bangalore, so thank you very much. So I'm going to, well, at the beginning, this talk was supposed to be more of the seminars type. Then I realized that there are many students. I was not very well informed about that before. So I added several slides that I think I can explain some stuff that were not said before about gravitational waves. So that's what I will try to do, is I will give a rather long introduction of various aspects of gravitational waves, either for transients or for the gravitational wave background. Then I will try to tell you, to convince you as a matter of fact, that we can use gravitational waves in order to test various models of astrophysical origin for compact binaries, for models of particle physics beyond the standard model. And I will give 2 examples. The case of first order phase transitions, a lot has been covered there, so I will just go to the results that we have found, and cosmic strings. Then I will discuss how you can use gravitational waves in order to get information about early universe cosmology. And I will discuss about second order scalar perturbations that again has been covered or will be even more covered. And then about the stiff equation of state. Then I will discuss a large scale structure from gravitational waves data, which means directional searches. And at the end, I will say a few things about how we can use transient gravitational waves to study the type of dark matter we have, whether it is cold dark matter or interacting dark matter. And I will also consider 2 cases of dark matter candidates, primordial black holes and axion-like particles. And then I will talk how transient gravitational waves can give some idea about testing theories of gravity, classical or quantum. So the introduction, gravitational wave signals and the gravitational wave background. So just to remind to people, the first indirect detection of gravitational waves was done many years back in 1974 by Hulse and Taylor, which is the millisecond pulsar. More precisely, you have these pulsars, which are neutron stars that they spin very fast. Their mass is about 1 solar mass, 1.4, 1.2, 1.36 solar masses in an elliptical order with an ellipticity point 617. And what was found is that exactly the change in the orbit was exactly the release of gravitational waves with energy density, what is given by taking Einstein's equation. So that was the first indirect, however, detection of gravitational waves. Now, the first direct detection of gravitational waves was thanks to the LIGO interferometers that goes back to 2014. So that was on the 15th of September of 2014. This is the GW 170914. So what it was found, it was this kind of remnant of the gravitational waves from the collision of 2 black holes of about 30 solar masses. And here you can see what was the result and what was the prediction that we had from the simulation. So here, okay, you can see actually, you can even hear, but the voice doesn't work, the sound doesn't work, of the chip that was detected from the 2 LIGO interferometers. Okay, now, the way that the interferometers work is you just send a laser light along the arms of the 2 detectors, which they have exactly the same length. At the end, what you have, then it is split, as you can see, and then it follows the same path of the arms of the detector. At the end, you have the mirrors, it is reflected back, and then if there is no gravitational wave, then by construction, the time that takes for the light to go back and forth is the same. They will arrive at the same moment. They have been constructed so that if they arrive at the same time, then there is no signal. But if there is a change because there is squeezed or stretched by the gravitational wave passage, then it's going to be a kind of signal which you get. And by studying this signal, there is a dephasing, as a matter of fact, by studying the signal and going to make the comparison with what we call match filtering techniques, where we have exactly the signal that we expect for a given merger. In other words, if you know exactly the mass and the spins, you can go and read and find what are the properties of this kind of source that gave the gravitational wave. Now, here I will basically, whatever I'm going to say is going to be for terrestrial interferometers, mainly therefore for the LIGO Virgo, in Kagra to some extent, which is the same kind of, basically is the same type of interferometer, even though it is underground. And it could be applied to third generation interferometers like Einstein telescope and Cosmic Explorer. So it's not automatically valid for LISA. So here are the detectors, and I will refer to which kind of mergers we can detect with the frequency that we have with these detectors, which is about the kilohertz, okay? So the second important kind of detection of the collaboration was the binary neutron star, which was followed a few seconds afterwards by an electromagnetic counterpart. And this was the beginning of kind of multi-messenger astronomy. And that was extremely important because even this one single event that we had, we were able to put constraints on the speed of the graviton or consequently on the mass of the graviton. So that were the two important kind of detection, and then they were followed with 100 kind of public events. Now we are in the fourth observing run, and we have various events that come up, and this observing run soon is going to end, and you would expect the first papers of the collaboration to be about in August. Okay. Now, something that I would like to say so that people can keep that in mind, there is a very simple kind of calculation that you can make and tells you why the gravitational waves are so weak. The fact that they're so weak is that is the difficulty that you have to detect them. So if you take the fact that it's just the amplitude, what we call the strain of the gravitational wave, is just given by the fractional change of the length of the detector. If you write down the quadruple formula, which is the typical one you use for the inspiral, then this is the expression you get, okay? And immediately, this term here is what it is numerically extremely small, and that is the reason, basically, for which you have that the strain, in other words, the amplitude of the gravitational waves is about 10 to the minus 21, is thinner than a human hair, okay? So, now, another thing that I would like to say as well that will specify with the LIGO Virgo Kagra interferometers what is the type, the mass of the black holes that we can detect is that if you consider a binary system, can be binary black holes, binary neutron star, or black hole neutron star, then the frequency of the gravitational waves, it is determined by how quickly the interacting objects orbit around each other. And actually, the frequency of the gravitational waves is twice the orbital frequency, which means if I take two black holes of a stellar mass, they orbit once per second. That means they have a frequency of 1 Hertz. That means they could generate gravitational waves of 2 Hertz. If you take two black holes that they move pretty rapidly around each other, 500 times per second, they generate a gravitational wave with a frequency of 1 kilohertz, which is exactly the frequency range of LIGO Virgo Kagra. That is why we say that these interferometers we have today, they are able to detect gravitational waves of this higher range of frequencies. Now, I would like to give this kind of classification of the morphologies of the gravitational wave signals that will tell us which kind of source have produced them, and what is the technique that we use in order to detect them. So we can separate them in the following way. They can be transient or persistent. In other words, do they appear in your interferometer as long as the interferometer is switched on or not? They can be phase coherent or phase incoherent. You do not know the phase of the gravitational waves. Can you therefore model the phase in a deterministic or in a non-deterministic way? If you classify them like that, then you have different kinds of sources. Transient, phase coherent are exactly what we have seen with the compact binary coalescence. If they are persistent, phase coherent, then they are continuous waves. If they are transient, phase incoherent, then it's like burst that you have from the collapse of supernova. And if you have this kind of persistent phase incoherent, this is the gravitational wave background, originally thought that goes from a cosmological origin. So depending on which part, which corner of this thing you are, there is different kind of origin, and that means different ways of going for the detection. So if you are in the case of phase coherent, then you use the match filtering techniques. What does this mean? As I said before, you have a bank of waveforms, depending on what are the properties, basically the mass and the spin, if we are talking for black holes, okay? And then you are going to compare what the interferometer gave you with this bank of models. And then you see where you do the match, and that is going, from there you read the parameter estimation. That I simplify the whole thing that works. Now, in the case of persistent phase coherent, this approach is not working. Why is not working? Because it's very difficult to make a separation between the noise of your instrument and the real kind of signal. But if you are in the case transient phase coherent, this technique works very well. You can make the separation from the difference of the arrival time that you have of your signal in your detector, and there is no, therefore, surprise why all the data that we have so far, this 100 of detection I said before, they belong exactly to this corner, transient phase coherent, which means emitted by compact binary coalescence. Now, what are the techniques that we're using for the CBCs, this compact binary coalescence? So there are three kinds of phases that you have. The first is the in-spiral. The in-spiral is when there are pretty long separation between each other and the gravitational field is weak. In other words, if I go in this kind of diagram, this is the sorted radius for a black hole of mass m, okay? Then if I am near this kind of axis, that means that I have really very weak fields. If I'm near this axis, that means that they move very slowly. So exactly this area, it gives you slowly moving, weakly self-interacting objects, where this relation exists, is valid. You can very easily write down this relation, where this is the Schwarzschild radius, okay, this is the separation, and this is the speed with respect to the speed of light. So in that case, we use post-Newtonian methods. What does this mean? That means that you are going to introduce this small dimensionless parameter. As I told you before, this is the relation that you are going to have, which is given, was given in the previous expression. You wrote down Einstein's equation, you perturb Einstein's equation, and then you have to expand it in all these orders according to the expansion in this epsilon quantity, the geometrical part, which will be given from the various components taken actually from the metric and the energy momentum tensor, and then you can get the various post-Newtonian order of the expansion, and you obtain these equations. Now, there is, at some point, this in spiral is no further valid. So you have to consider these black holes in a sorted kind of geometry, and that means that there is a distance below which you cannot anymore have a stable circular orbit of your system. This is called the innermost stable circular orbit, or ISCO. It is given by this expression. You can solve it easily, but I'm not going to prove these things here, where m is the total mass of your binary system, okay? And then once, if you go up after this kind of coordinate distance, then the two objects of your binary system are going to merge, and at that point you have that the second phase of this CB sequence is going to happen, which is what we're calling the merger. And the corresponding kind of frequency for this innermost stable orbit, it is given here in terms of the total mass of the binary system, okay? So if you put some numerical values, then for about a solar mass of a compact binary object, then it is at about 2.2 kilohertz, this frequency. Now, if you reach that point, then you have the merger, okay? Now, the merger will depend very much on what is the nature of these objects, okay? So that's something which here you cannot be actually generic. Then we have a small separation between the two objects, and we have therefore a strong gravitational field. The speed is close to the speed of light, and here we're using numerical relativity. And finally, at the final step, we have the ring down, where actually the system is going to relax to a final kind of stable object. Usually it's a black hole, and all extra kind of oscillations are going to emit gravitational waves, and in that kind of final step, we're using perturbation theory. So this is the typical kind of tools that they are used for the three phases of the compact binary coalescence, okay? Now, here I would like also, because it becomes very fashionable nowadays to become about dictionary, about the machine learning techniques or whatever, I would like just for people who are interested, for students who are interested about that, there is a very acute problem which will arise, which means the number of data we have increases very, very fast. And in particular, if we would like to say there is an electromagnetic counterpart and we would like to go and say to our colleague who has a telescope, go to see there, we have to do it fast. This parameter estimation that I told you before, it takes about a day. A day is long. And the data become too much. They are already many, but they increase, the volume of the data is going to increase very fast. So we need to develop a technique that is not going to be up to now, is not as precise as the standard parameter estimation that the collaboration uses, but we would like to have a pre-screening that tell us this is junk, leave it out, and somehow leave just a few candidates for which we can do the parameter estimation. So we develop a technique for the case of LISA, because somebody mentioned that the other day, I don't know who was talking, about the LISA. LISA is going to be contaminated by white dwarfs in the disk of the galaxy. And that will be a problem. So we developed a technique, which is a machine learning technique, because we know what will be the waveform of the white dwarfs in order for LISA to do the separation. And now we use this approach for the MRIs, and we're using this approach as well for a rapid kind of pre-selection of data that are worth to go through parameter estimation. So the collaboration takes very seriously, but in a very kind of conservative way still, any kind of machine learning techniques, even though I was in a meeting in Banff 2 months ago where that was the topic, how we can be sure and how we can develop techniques that will help us to deal with a huge number of data that we have. So for people who are interested. And then the last thing is the stochastic gravitational wave background. So the stochastic gravitational wave background is if you wish, okay, so this is the corresponding of the electromagnetic background that you are all more familiar from the cosmic microwave background, okay? And the ultimate goal that actually we have is to reproduce a kind of a map of the sky, which is not this temporary kind of fluctuation, but is the fluctuations in the density of gravitational waves. So at the beginning, as a matter of fact, people thought that the gravitational wave background is going to be of cosmological origin, after inflation or after phase transitions of defects or quantum gravity, whatever you want. That is why it has been used to determine how much gravitational waves you have of this dimensionless parameter, which is the standard kind of people we use in cosmology, omega Darmstadt, omega baryons, omega photons, whatever. So it's the omega of gravitational waves, is the energy density of gravitational waves, normalized in logarithmic interval of frequency, normalized by the critical energy density. And the energy density of gravitational waves goes like the square of the time derivative of the amplitude of the tensor perturbations. Now, on the top of this cosmological background, there is an astrophysical background, which comes from sources which are very far away, and they are very weak, and therefore you cannot really identify them. It's like if you go to listen to a concert, and you cannot make the distinction who plays the violin, who plays the contrabass or whatever. So it's the same thing. So we have a superposition of gravitational waves from sources which are far away of an astrophysical origin. And one big problem is if and when, actually not if, when we're going to have a detection to be able to make a separation between astrophysical and cosmological origin. Parenthesis, with current detectors, we cannot do it. So, and usually, the energy density of gravitational waves given by this dimensionless parameter, okay, it has a frequency dependence, and this power law depends on what is the source of gravitational waves. I will show you in a few minutes. If we're talking for compact binary coalescence, it's 2/3. If we're talking for phase transitions, it's a broken power law. If we talk for cosmic strings, it depends on the frequency, but for the range of the frequencies of our detectors is almost flat, which is the same as for inflation. So the frequency dependence will depend on the origin of the source. Now, these gravitational waves, they propagate through a background which is perturbed, okay? Which means if we have a gravitational wave background of a cosmological origin, is going to lose any phase coherence, which was at the beginning of their formation, of their emission, or when they enter the horizon. If we have a gravitational wave background of an astrophysical origin, then there is no phase coherence there as well. For it has been shown by these people that for standard cosmological model, there is complete loss of coherence for frequencies above 10 to the minus 12 Hertz. So that's what we consider. So let me write down the strain, the amplitude of gravitational waves in Fourier space. That's why I put this tilde, and depends on the frequency. This is a complex number, which is given here by the amplitude, what I call the strain, and the exponential of phi with phi to be the phase. I said that the phase is random, okay? So this vanishes. There is no phase information. So the only information that you are going to receive, it comes from the amplitude. And for the simplest, for the first part of this talk, so before talking for directional sources, everything that I'm going to say is going to be the standard assumption that if I have the 2-point correlator of the strain in Fourier space, the tilde, A and A prime are the two polarization modes. In principle, it depends on the frequency and in the direction and from where the gravitational waves come by, okay? This is a normalization factor. This is the Hubble constant. This is the frequency. Now, for the first part of the talk, I'm talking about an isotropic background. So there is no dependence on the direction. It is unpolarized, it is stationary, and there is no phase correlation. Not all these assumptions are always valid, but this is the assumptions, the typical assumptions that we're making. Let me now specify what I mean by that. It is unpolarized, which means the gravitational wave radiation has statistically equivalent plus and cross polarization components. It is stationary, which means that all the statistical quantities depend only on the difference between times and not in the difference of the time of origin. This is not always valid, and this is certainly not valid for the noise. Then I consider that is Gaussian, which means all information I want will be up to the 2-point correlator. This is not for all sources always correct, but that's the standard thing that we're making, okay? So here is the strain as a function of the time, a typical kind of result that you can have for the gravitational waves for a Gaussian gravitational wave background. So now I have to continue with these introductions. Now, because I will use these things afterwards, I will consider always Gaussian, stationary, and polarized, special, homogeneous, and isotropic. So the two-point correlator of the strain is expressed by this way here. Again, as I told you before, this is the stationarity, this is the fact that it's unpolarized, and this is that it's homogeneous, where this S that appears here, it is the one-sided gravitational wave strain, which is related like that to the amplitude of the gravitational waves. I'm saying that because sometimes I'm going to write down the strain. I'm going to say this is the gravitational wave strain, so I have to define what it is. And now, when I'm going to consider, in the second part, or at some point during today or on Thursday, when I'm going to discuss directional searches, that means that we have here the power spectrum, which it depends not only on the frequency, but as well on the direction. And the total gravitational wave strain, it will be just the integration over all frequencies. Sorry, all directions. If you want all frequencies, then you have to take the integral over all frequencies as well. Now, and the relation which you have, remember I discussed before about the dimensionless quantity omega GW, which gives you the energy density of gravitational waves in the logarithmic interval of frequency. The relation which exists between this omega GW, which is defined again here, and the strain, this definition I gave before, it is given. So you can go from the one to the other, basically by just introducing an f to the cube factor in this numerical stuff. I'm saying that because in the literature you can find equivalently these terms to be exchanged, and also because I will refer to both as we go along. Again, if you want to find the total energy density, then you take you integrate over all frequencies with minimum and maximum frequency, which are the frequencies at which your interferometer works. Now, here again, there are more definitions, which again, what we said before. So let me just go to that again, because this is very important, that you have the strain to depends on the frequency like a power law, with a law which depends this power depends very much on what it is the source. So I just write down what I told you before. For an inflationary gravitational wave background, then the frequency dependence here is flat. For compact binaries, I will show to you in a second. You take the inspired formula. This is 2/3. Phase transition is a broken power law. Now, what you do in order to calculate the energy density of gravitational waves from compact binary coalescence, this is a very important formula. That's why I wrote it here, but I will write it as well later. The very important parameter which exists is this here, R. This is the rate of mergers, okay? You calculate, it's pretty complicated to calculate the rate of mergers because it depends very much from when the binary has been formed, when it has been, from the start, you start from the start, you have to go when the compact was formed, when the binary was formed, when it's going to be merged. So there is a very rich astrophysical kind of complexity that comes there, and depends on the parameters, and the parameters theta is given here. For instance, for black holes, it depends on the mass and the spin. Then this very important quantity here, which gives you the energy density of gravitational waves in a particular frequency, and that depends on the masses. You put all the cosmology you want to take into account in this function E. Usually you take the lambda CDM model, and you have this redshift factor. So this is the way that you calculate the energy density of gravitational waves from compact binary coalescence. So here I give you a nice kind of just of figure where you can see the various types of sources that can lead to the gravitational wave background. the corresponding wavelengths at which this background exists, the corresponding period, and what are the experiments that we use in order to detect it. So where we are now, we are in the case of LIGO here, so we're talking for about kilohertz and about, you know, in mass of black holes of about 50-100 kind of solar masses black holes. So what are the detection? What are the methods to detect gravitational waves? Again, I have to give you a lot of background here. I'm talking about the gravitational wave background. And the problem which exists, the main problem that we have, is that the noise is much, much stronger than the signal, okay? So if you try to detect it with just one interferometer, you are stuck, you cannot do it. So what we do is we combine the outcome of two detectors. And thank God we have 3 detectors, okay? Even more as here will come. So here it is, the detector 1, okay? It will give, there is a signal and there is the noise. A detector 2, so you can take LIGO Hanford, LIGO Livingston if you want. For both of them, the signal is the same, but the noise is different. And then we cross-correlate the outcome of the 2 detectors. Now, by assuming that, which is a very normal, I mean, it's a correct assumption, that the signal and the noise are uncorrelated, then this correlator that you built is just the signal and the correlated noise of the 2 detectors. So in general, up to the second observing run, it was considered that there is no correlation of the noise of the 2 detectors. We know that this is not correct. We know that there is correlation of the noise of 2 detectors. For instance, we have what we call Schumann resonances. There is correlation of 2 detectors. We know how to treat it. It has been from the 3rd observing run and onwards, we know how to search for this correlated magnetic noise, okay? But what I would like to say is that by correlating the outcome of 2 detectors, we can find a way to have the signal. And this, however, it's an example of something that cannot be applicable as it is for LISA, okay? So you have to use other kind of techniques because there we cannot correlate the outcome of 2 detectors. That's why I said at the beginning that what I'm saying is strictly for what we are doing now for terrestrial or 3rd G detectors, but not automatically applicable for LISA. Yeah? Yeah, we know how to do it. We have developed with a student of mine, as a matter of fact, a technique which now is used by the collaboration. It's called the Schumann resonances. We know how to do it. It is used, still is below the sensitivity of the detector, so there's no problem, but we know how to deal for that. So now I have to tell you what we call the detector response, right? Because it's something which, all these are quite important because, you know, for instance, remember what probably you have seen in courses. You take this ring of test particles, okay, and you take the XY plane, and you say that I have a gravitational wave come in the Z direction, and then you see how these test particles are going to change depending on the polarization. Very good. But in practice, this is never going to happen exactly like that. You are not going to have this alignment of your detector. So you have to take into account that there is going to be a decrease. I mean, the capability of your detector to detect is going to be decreased because of the particular orientation of the detectors you have. And that's what we call the detector response. Okay, so here is exactly the same Michelson kind of interferometer as I said before. This is the round trip of the photons along the arms of the detector. So what you call like detector response is that the phase, okay, which I can write it like the difference in the phase, this phi, is going to be 2 pi times the frequency of the light of your laser and times the difference of the time of the two, the splitted kind of laser beams to go across the arms of the 2 detectors. That means that the strain can be, which is by definition the fractional change in the length of the detector, it can be written like that in terms of the difference of the time that takes to go back and forth from the two arms. And therefore, you express the strain of your detector, which means you express the strain of the tensor perturbation, the amplitude, in other words, in terms of this kind of response function of your detector, which depends on the frequency and the direction. This is the metric perturbation. So that's what you have to take into account if you're going to write the metric perturbation in terms of the strain with the response function of the detector, which will depend on the characteristics of the waveform that you will receive. Now, going back in what we said before, I take my two detectors, I and J. These are my data. This is my response now of the detector. So it's not exactly the strain that we said before. It's not exact, but it is what the detectors indeed are going to measure, plus the noise. You play with this two-point kind of correlator. And then if, as always, we remain within stationary, Gaussian, isotropic, and unpolarized background, then the two-point correlator of the response of the detectors I and J can be written in terms of the strain, which I have defined before, which basically is omega over f to the cube, in terms of this gamma ij, which is called the, this we have defined, the gamma ij, which is the overlap reduction function, okay, which is exactly the reduction in the sensitivity of your detectors, which depend on their orientation and their geometry. And this is something that will depend which detectors you take, for instance, depending on whether you take, like I don't know, here I have different kind of detectors, and the ET, I can give this function. That's something that we take into account. And you will see in a minute how this is going to enter in the calculation. Okay? I'm doing this time. So now I would like to discuss for the signal to noise ratio, and I'm going to tell you that the signal to I'm going to prove that the signal to noise ratio can be arbitrarily large as long as the time that you do your observation becomes arbitrarily long. Okay, so here is the data of the two detectors, okay, as we said before. So the two-point correlator of the data is actually related with the energy density of the gravitational waves. Let me now consider that I have n measurements, okay? And now, if you assume that both the signal and the noise are Gaussian, I told you before that this might not be always the case, then this is the variance, and from there you can go and write it down, the signal to noise ratio, which it is simply, you can calculate it to find that it goes like that, which means that in the weak signal limit, what you are going to get is that this factor is very small. So basically you have that the signal to noise ratio, okay, depends on the number of the measurements, and the number of your measurements depends actually to how long the observing time is going to be. Therefore, from this part, because this is negligible, you find that the signal to noise ratio is proportional to the square root of the observing time. So if you take that arbitrarily long, you are going to pay the signal to noise ratio as high as you wish. Which means that for a gravitational wave background, if you consider the signal to noise ratio for one event is extremely small, but if you combine the signal to noise ratio of all the data that you have, then it becomes much bigger. For instance, as you can see here, if you wait about 40 months at the design sensitivity, you have a signal to noise ratio equal to 1. Yeah. Yeah.
So, I mean, let's say you have a really low data and you still in 10 chunks.
Yeah.
I mean, if the noise was calculated in 10 chunks, you wouldn't need to second. I mean, then even measuring one experiment would be good enough.
Yeah, but then the signal to noise ratio is extremely small. You have to combine these, otherwise, you see, it goes as the square root of the observing time. That's why what we actually do, we consider as well data from previous runs that in order to increase the number of data we have. The more data you have, the better signal-to-noise ratio you have.
Correct. Let's say you have a long time, you put it in 10 chunks.
Yeah.
Then the signal-to-noise ratio will also go to infinity if you have more chunks.
No, because they are the same. Then they are going to have correlation between those.
This was the question.
Yeah,
noise correlated between
yes,
bunches.
yes,
Okay.
yes, yes. That's the problem. That's why you don't do it that way. So now I would like to tell you exactly what you do. So I needed all these factors that I told you before. So let me take that I have my 3 detectors, the 2 LIGO and the Virgo detector, and I built this estimator. I built this 2-point estimator. This, I work in Fourier space, that's why the tilde. I and J are my 2 detectors. This is the normalization we said before. Remember, is, as we said, omega divided by f to the cube. This is the gamma ij that I told you before, which is this kind of a geometrical factor that depends on the orientation of the detector. And this t is the time of your observation, okay? Now, we have to be careful with, is actually the chunks that you said before, how you cut them, and the fact that the noise is not stationary, but that's basically is a detail for what we say here. And then we built the 2-point correlator. You have this estimator here. And as we said before, by putting that equal to 0, in the case that there is no noise correlation, then this estimator is actually, in the absence of correlated noise of your detectors, is the energy density of gravitational waves. If, however, there is a correlated noise, then you have this term as well, which you have to take into account. So that's the base, that's the way that we search within the collaboration for a gravitational wave background. Now, a thing that you have to know is the sensitivity curve. I will give some plots and I will say this is the sensitivity curve, which actually is basically called the power law integrated curve. So remember, we said that the energy density of gravitational waves, omega GW, depends on the frequency with the power law, with the value of the power law, depending what is the origin. So what we do, we take various values of this beta, the power law, and for all these values, we go to make in a logarithmic plot omega GW as a function of the frequency. The envelope of this omega GW is the power law integrated curve. In other words, mathematically, this is the definition of the power law integrated curve, which means that if you calculate with your model a curve which is tangent to this power law integrated curve, the signal to noise ratio is equal to 1. Then if it's small, if it's above or below, you have the signal to noise ratio above or below 1. Okay, that's the power law integrated curve, which is called otherwise sensitivity curve. So, and the last thing.
So, detailed question. So you said before that for phase transitions, you have broken power law.
Yeah.
Do you think that it would be interesting to build broken power law sensitivity curves?
No, because it could, but otherwise you are going to do it in each of the 2, you know. Yeah. As a matter of fact, the majority of the times, what you find is below. So we have not reached that. We have not reached. If we reach, when we reach it, probably what you suggest could be important. I have not thought about that, I admit, and I think nobody has done it, but it's a very interesting thing because all the values we take now for beta do not consider broken power law. Consider -3, 2 + 3. This is the range. But what you point is very relevant. It's a good remark that probably will, yeah. So now the last thing I have to say as a background is for the statistical inference, because it's the frequentist and the Bayesian kind of approach, which we use when we want to do this parameter estimation. So the statistical inference is basically what it tells you. You ask whether there is a gravitational wave signal in the data, and then you want to find what is its parameters, what we call parameter estimation. So you have these 2 approaches. At the beginning, within the collaboration, was the frequentist approach that was used. Now everything goes more towards the Bayesian approach. The frequency probabilities are related to the frequency of events. Bayesian probabilities are related to the knowledge that you have about an event. So I will take an example to infer the mass of a star. So if I take the case of frequentist approach, then the star has a true mass. It's fixed. We don't know what it's fixed. So the uncertainty in your data is given by the the probability, what is called the probability distribution in observing the data, given that you have that mass. If you consider the Bayesian inference, in that case, you know the data, and the mass is what you are not that certain about. So what you do here is you find this posterior probability. The mass has a certain value given the data. The relation between the probability distribution and the posterior are given through the Bayes theorem, where these things are the prior probability distribution of the mass, and this is the important thing to consider when we use the Bayesian kind of approach, whether our results depend crucially on the priors that we have considered, okay? Because often this is a weak point. So these are the two approaches that I use, and I will say that because much later when I will put constraints that we have found for the case of cosmic strings, I will talk about this posterior probability and the Bayesian kind of approach. So now, last thing to say as a background is the optimal filtering. So here is exactly again what we construct. We construct what we call an optimal estimator to search for the gravitational wave background by considering this quantity here. So we combine the cross-correlated from different frequencies, you can see here, and then we take the sum of the frequencies, okay? And we have this weighted factor, which is given here, is the omega GW frequency with respect to omega GW of a reference frequency. The best frequency at which LIGO works is 25 Hertz. So that is the one by which we normalize our data. Okay. And then we take the sum of the pairs of all the detectors that we can use, okay? So in order to increase the number of data that we have. Now, to find the parameter estimation, okay, this is the likelihood which we use. Theta are the parameters of your model. Let's say that I'm talking about black holes. The parameters are the mass and the spin. This here is what LIGO gives me. This is what the data gives me. This is what me, as a theorist, I have calculated given the parameters. When I'm going to talk about cosmic strings, for instance, here my parameters will be the loop distribution and the tension of the strings. And then my model, my theoretical model will give me that. And the data of the collaboration will give me that. That's how I go and I calculate the likelihood. And that is something that we discuss. I will refer to that later on. Okay, so in the third observing run, it was the first time that we combined the outcome of the theta detectors. We built this two-point correlator that I said before. That's what we found. So we cross-correlate. We found this optimal kind of estimator that I discussed before, which I call it C, that depends on the frequency, and that's what we got. So exactly that tells you that the spectrum is consistent with expectation from uncorrelated Gaussian noise. So there was no detection made, okay? And we have found that as well, there is no relevance for the correlated magnetic noise. Now, even though this has not been detected, you can put constraint on your models. So the constraint that exists for compact binary coalescence then is smaller than 10 to the minus 9, which means if the frequency dependence goes like 2/3. But you should not be surprised that has not been found yet. It is already 4 orders of magnitude below the CMB. The CMB is 10 to the minus 5, we're 10 to the minus 9 already. That means that we are pretty, it's pretty low. I don't think that we will detect it now in the fourth observing run, but I'm quite optimistic that in the fifth observing run, we might find it, presumably from astrophysical sources. Now, if you go with a spectral index of 3, which is for some cases of supernova, this was found, then it can go, this is the limit we have. If we have flat power spectrum, which can be for the case, for instance, of inflation of strings, then this is the constraint that we get. So now I'm going to talk about how this can be used for a gravitational wave background information about astrophysics. And then I think I will stop for today and I will continue the rest afterwards. So here is exactly what I told you before. Okay, so this is the basic formula that we have to use. This formula will be different when I will do, for instance, for the case of cosmic strings or for the case of phase transitions. For compact binary correlations, this is the form that we use. This is what I told you before, the rate of mergers. This is the Hubble parameter. I take the standard lambda CDA model. This is the important quantity to take into account, which is the energy density in an interval of frequency, which is radiated for a particular model, okay? And now this actually quantity here, as I told you before, depends very much on the astrophysics that lead to the formation of these compact objects, okay? And on their parameters, not only on their parameters, which I denote by phi, like the mass or the spin, but as well on the evolution of the stars that lead to black holes, that lead to the compact binary, and so on. So this is the astrophysical model, okay? And therefore, in the collaboration, there is a canonical astrophysical model which is used. I'm not going to go into detail. And we have studied deviations of that model. And when I tried to ask my colleagues which is the correct model, the answer I got, it was, once we detect it, we will know. Because we don't know it, because it depends on that model, okay? And then we go up to a redshift of maximum 10, because astrophysicists don't believe that these compact objects will be in a higher kind of redshift. And we consider 3 classes. This K here represents the class of compact binary, can be binary black holes, binary neutron stars, or neutron star black holes, okay? Now, so now this is what let's take, let me see what I have afterwards. Okay, here is the simple thing that is going to take to show that we have the frequency dependence of the omega GW like to the third. So I take the energy spectrum will be determined from the strain waveform of your binary system. The energy released of gravitational waves as a function of a frequency depends on the chirp mass, which is nothing else than the combination of the masses of the binary. This is the total mass and this is the reduced mass, and it depends like that on the frequency. Immediately from here, you see that once you integrate overall frequencies, you get the 2/3, okay? Now, a note, for the case of the binary neutron star, okay, we consider only the in-spiral phase. We do not consider the merger, we do not consider the Rig-down. Why? Because merging of neutron stars are at the 2 kilohertz range, and this is above the sensitivity of our stochastic search. For the case of binary black holes, then we include all 3 phases of the collapse. So here is the case of compact binary coalescence. So remember, I repeat it once again, because it's simple and it's nice to be able to do it easily. Omega GW depends of the power law frequency dependence. You write down this expression. As I told you before, the energy density in an interval of frequency goes like f to the -3rd. You integrate over all frequencies, you find that goes like f to the 2/3. Okay? So for CBCs, this alpha is 2/3. So here, these are the sensitivity cases. What I discussed before, the integration that I said before, and these are for the different kind of runs we are. So for instance, the O3 is this black bold face. The design is here, okay? We are somewhere in the between now. Then you take your theoretical model, okay, which will depend on all this astrophysics. You go to calculate, and remember what we said, you're going to find a curve like that. If it is tangent to the sensitivity curves, that means you made a detection with a signal to noise ratio equal to 1. We are below. The best sensitivity of the detector, I told you before, is 25 Hertz. You see, we are below, and this kind of shaded region is just the astrophysical uncertainty. You take different models, you go to calculate, and that's what you find. So that is what we have found as a constraint for the case of a gravitational wave background from compact binary coalescence. Okay, now, then, even without changing the astrophysics of the formation of the compact objects, we said, let us play with the mass and the spins, okay? And let us take some thousands of different kinds of ranges. What we have found that several years back, I mean, whatever by now, we have found that the omega GW is going to be changed by almost 2 orders of magnitude, which means the day I will find the gravitational waves, I will be sure that this background has nothing to do with noise. I'm sure that comes from compact binaries and has no contamination from cosmological sources. I will be able to find something about the population of compact objects. And that's something that, as a matter of fact, now in the current run, in the stochastic group of the collaboration, people explore various astrophysical models to see how they will impact the detection, or not the detection, how they will impact the result of the omega GW. Now, there are, however, possible complications that I would like to mention before I finish this part. All that I said is for standard stars, what is called population 1 and population 2 stars. Somebody mentioned here the other day that they might exist population 3 stars. These are stars in very high redshift that they could have been produced. They are basically made out of hydrogen. They have very high redshifts. These are called population 3 stars. They haven't evaded any kind of constraint so far, and there are speculations that this could be at the origin of supermassive black holes. If these objects exist, the 2/3 law that I said before breaks down. Is not valid anymore because you do not see them during the inspiral phase. So the calculation is not further correct. What is the correct? We don't know. It seems to be like a broken power law, but we don't know exactly because there is a disagreement in the astrophysical simulations about population 3 stars. Second kind of thing. I said always that I consider Gaussian, okay? But this actually is not correct because for the frequency band of our detectors, the gravitational wave background from compact binary coalescence is most probably not Gaussian. What do you have to go to calculate to see whether it is or not? You have to go to study the ratio of the average time between events to the average duration of an event. If this ratio is small, that means that you have many events arriving all together, which means that the signal is like a continuous signal, which means that this Gaussian distribution is correct. If, however, this ratio is very large, that means that what you get is what people call popcorn, okay? So you have a discontinuous signal, and then there is a non-Gaussian probability distribution. There has been work originally by Eric Train in Melbourne about that, and there is some kind, and there are discussions within the collaboration to take that into account. But that's a complication that we said before. And then the last thing is about the anisotropies. And this will go up to now. I discussed that I have distributions which are have no, the energy density of gravitational waves have no directional dependence, but as a matter of fact, there is a directional dependence because you have a galaxy here, therefore a black here, and you have a void there. So therefore, this has to be taken into account. And this is something that we search for, and I will discuss. Okay. No, I don't want to say that here. No, so then I will stop here because the rest because then I will start a new chapter that I don't want to discuss now, which are the gravitational waves that could be give constraints, about physics beyond the standard model, about early universe, talking about the stiff equation of state, for instance, or parity violation as well. I can include something about that. About directional searches, which is the large-scale structure, and as well, what else I want to say? About models of gravity and about dark matter. So these are the things that I would like to cover afterwards. So I would like more to take questions if there are now about this part. I had another, 15 minutes, but that's okay.
About the function E that you assume lambda CDM?
Yes.
But now with all the story of dynamical dark energy, you think that
well, I mean, you know, there are many things that I'll tell you what's my personal view there, okay? So my personal view is that if I play with one side of Einstein's equation, I have to play with the other one as well. So if I go, the lambda CDM model, I mean, is GR plus that. If now I start changing that, some other things of the other side might change as well. And this, so then I have to go to the other side and see all the things about gravitational waves, how they will change, the formation of black holes, the stability of this double. So, you know, what I found a bit premature, even though all we have played with that, is you take a modified model, but then all the rest is the standard black hole physics, which is inconsistent. So this is the problem that I have. I think it should be, so from my point of view, at some point, one has to take these modified models of gravity, take the ones that there are somehow supported by some fundamental theory, whatever is that, then, and they are not excluded by now, and then to go to study the formation of black holes, the stability of these black holes, whatever change you have in the propagation, the formation and the propagation of gravitational waves, and then accordingly go to change the lambda CDM model. Otherwise, if you touch one without the other, that's my thing, and nobody does, but nobody does it. Because that would involve many PhD theses, even for one of all these things, which people don't do it. So I think that's the. And also, you know, because always people are more in the kind of let's say conservative approach. So we take what is more, even though lambda CDM now is not the more accepted thing, but yeah. Also because, you know, for me, gravitational waves is a probe of early universe, which should be used not as a consistency check of electromagnetic waves, but independent. So let's say that we didn't have CMB, we didn't have Koushik, we didn't have MAP, all these things. Use gravitational waves, then probably the lambda CDM was not going to be there. Now what we do is a consistency check.
More questions?
People are tired. Me too, actually. Now I will sit here. No, I mean, I was joking. Say.
About the power law integrated sensitivity and how you would expose this to a peak spectrum, like from the phase transition. How you would expose, or how would you do the analysis with a peak spectrum like the phase transition? I mean, you presented this power law integrated curve.
I mean, if I can go very fast to show you, let me show you something. Wait,
Didn't
I
you
need
ask
my
a question?
glasses to show you that. Give me 1 sec.
So what would be the idea, to do a dedicated analysis, or?
Because what we do now, I can go in, just give me a second, which I will discuss that. Okay, let me show you these things. Can I show? No, this doesn't show. What I did, does it show? Okay, so you see, for instance, what you can see here is a calculation of okay, so you have the standard quantities, you know, this alpha, beta, whatever, which exists. So then you can see that this is the design sensitivity, okay, the red, and now depending on these values, I'm here. So again, for me, for the purpose of what I do, if here you can see this, if it is tangent, this curve, that means that I made a detection. So the sensitivity curves are exactly, it is the envelope of this log-log plot, which has been considered in general for a power law, not a broken power law. I don't know how this will change because, okay, at any rate, you take the envelope of that. So if you take the envelope, it's the maximum of these things. So it's not going to affect probably too much. I don't know. That's my first reaction. And here is, you know, I calculate what will be the spectrum for these values. Forget them now of the phase transition. So given that is the maximum of these curves, I'm not sure that if I was taking a broken power law would have changed. But I have not thought about it.
I wrote a paper with a postdoc.
Yeah.
It doesn't change.
Doesn't change. Okay.
Change a bit,
but not okay. So you had the answer. Okay.
This is why I asked.
Yeah.
Okay, thanks.
So I have a question.
Yeah.
Just related to this here.
To relate to what?
Related to like the peak, when the peak of a FOPT lies, then how do we analyze with the power law integrated sensitivity curves? So I was thinking that if rather than having the peak within that region, if we just have the one of the power laws, say this one or that one, the rising or the falling one, would that be a more accurate one to describe using the sensitivity curve?
No. The definition of the sensitivity curve is what I said by construction. That's the way that is constructed. This, I'm not going to touch it. Okay. Because, you know, that's this is the maximum of that. And this is for any kind of slopes you can have. As I said, it was not done for broken power law. It was done for power law. But given that is the maximum, I think will not change much. Now, John Massimo said he has done it, doesn't change much. So, but this is the definition, which that's the way that you define the sensitivity curve.
And just one more thing is that it's not necessary to have it with SNR equal to 1, right? I mean, we can change that to any value.
Well, to a value which is acceptable, yeah. I mean, if it is above the SNR, the definition, if it's tangent, is 1. Okay. If it is above that, SNR is bigger than 1. If it's below than 1. I just gave the definition. You see. So now we have several orders of magnitude below, so there is no detection.
So I don't see any other hand raising, so maybe we can stop here, and thanks, Mairi, for the nice talk.